All right, let's take a look at Chapter 11b. And just like with Section A, 11b takes a look at math in a very non-typical sense. This one we're focusing on, instead of math and music, we're going to focus on math and the arts. So particularly we're going to look at perspective and symmetry, but really we're looking at all of how we use math in art. So there are at least three aspects of the visual arts that relate directly to mathematics, and those three terms are perspective, symmetry, and proportion. Oops, I have a misspelling there. So we'll look at all three of those terms today: perspective, symmetry, and proportion, how they apply to the arts and how they then also apply to math. So the next two slides, I have the same hallway picture. This one we're looking at it from one artistic's view. The other one we're going to look at from the other, and we're going to talk about why we care about this and what it has to do with perspective. But notice here, we're talking about if this person were to draw a picture of this hallway onto that canvas that you see kind of right here at that vertical blue dotted line, and how those pink lines are parallel in real life. They're the ceiling, the floor, the edges of the ceiling. They're parallel. But notice how when we put them onto that canvas to draw them, those lines are not parallel. That's what we can see by the dotted lines that are coming out of the eyeball. Let's take another look at a different perspective here. We've got P1 and P2, two different positions that we could be looking at it. It says an artist's view of the hallway showing perspectives. The lines L1, L2, L3, and L4, those are those pink lines coming from the floors and the ceiling, which are parallel in the actual scene, are not parallel in the painting. So kind of we talked about how that perspective changes from when we're taking what we're actually looking at and putting it into a picture. So let's talk about some vocab terms that help us define these types of situations where we're meeting or mixing math with the arts. It says lines that are parallel in the actual scene but not parallel in the painting meet at a single point P, and we call that the principal vanishing point. So when we have lines that don't meet in real life, but they do meet in a painting, we call that point where they meet the principal vanishing point. All lines that are parallel in the real scene and perpendicular to the canvas must intersect with the principal vanishing point of the painting. Lines that are parallel in the actual scene but not perpendicular to the canvas intersect at their own vanishing point, called a horizon line. So we can see that in this previous picture, again, the horizon line comes in right here across that center, does go through the principal vanishing point, and that's where those lines that are parallel in the actual scene but not perpendicular to the canvas, that's where those will intersect, or where they cross. So Leonardo da Vinci contributed greatly to the science of perspective. We can see da Vinci's masteries of perspective in many of his paintings. If you studied The Last Supper, you'll notice several parallel lines in the actual scene intersecting at the principal vanishing point of the painting, that first term we had on the last page, which is directly behind the center figure of Christ. So we can see here these parallel lines in real life across the ceiling or along the floor are meeting at that principal vanishing point right behind the head here. The German artist, I think his name is Albrecht Dürer, further developed the science of perspective. The next slide shows one of Dürer's woodcuts showing an artist using his principles of perspective. A string from a point on the lute is attached to the wall at the point corresponding to the artist's eye. At the point where the string passes through the frame, a point is placed on the canvas. As the string is moved to different points on the lute, a drawing of the lute is created in perfect perspective of the canvas. So this is a really neat way to scientifically get an exact, using the exact perspective needed to have this drawing of the lute. So just kind of a really neat thing that dates all the way back to the 1400s and 1500s. So that's perspective. Symmetry refers to a kind of balance or repetition of patterns. In mathematics, symmetry is a property of objects that remain unchanged under certain operations. Symmetry is probably something you've talked about from early on in grade school through middle school and then again in geometry. So we're just going to kind of quickly review that. When we talk about symmetry in mathematics, we talk about three different types of symmetry. The first is what we call reflection symmetry. And that's when an object remains unchanged when it's reflected across a straight line. I think of this as like fold symmetry. If I could fold that object anywhere along itself and the left half matches the right half or the top matches the bottom, however you're folding it, then you have what's called reflection symmetry. The next type of symmetry is what we call rotation symmetry. And that's when an object remains unchanged when rotated through some angle about a point. So it doesn't have to be unchanged the entire time you're rotating it, but if you can rotate it a specific amount of degrees and it stays unchanged, then you have rotation symmetry. I like to think of this as turn symmetry. If you can turn the object and it stays the same, at some point you've got rotation symmetry. And the last is what we call translation symmetry. Oops, I'm going to change colors here. And that happens when we have a pattern remains the same when shifted to the left or to the right. So this picture here of those multiple, it looks like capital letter X's as you move them left and right. They remain unchanged. That is translation symmetry. So let's go take a look at a picture here. We've got, it looks like a 5-point star. We want to identify the types of symmetry in the star. So we want to identify whether we've got reflection and or rotation and or translation. So remember, reflection symmetry, think of it as your folding symmetry. Could we fold the star anywhere and have the left half meet up with the right half? And if we went right down the center from this point to that point, if we folded that right to the left, we would certainly have it lay upon itself. And that's what we call reflection symmetry. And in fact, we have that going on multiple places here. Anytime I go through a point to its opposite, we end up with reflectional symmetry. So we can certainly say we have reflectional symmetry. I'm just going to say reflection symmetry rather. Notice though, if I were to turn this a fifth of the way around from that first top point to the second point, I would have the same picture again. That entire star would fall upon itself. And the same here, turn it again, again, and again. So I also have rotation symmetry. I do not, however, have translation symmetry, as I don't have any sort of tiling going on. I don't have any sort of repetition from shapes. If I move this left or right, up or down, it's not going to fall upon itself. There's only the one picture there. Now, a term I just referred to, probably something that's not a brand new term to you, but what we call in math a tiling, is an arrangement of polygons that interlock perfectly without overlapping. So you've got 8 pictures there of examples of tilings. It doesn't have to be the same shape repeated, but we can't have any overlapping, you can't have any gaps. So for example, you couldn't simply take a circle and tile it. You put 2 circles next to each other or 4 circles next to each other, there's going to be gaps in between them. So it takes a specific type of polygon to be able to tile. Some tilings use irregular polygons. So let's define what regular polygons are first so we can talk about irregular polygons. A regular polygon means it has all equilateral sides and equiangular angles, or all the sides and all the angles are the same. But we can do tiling with irregular polygons as well. Typically we have regular polygons because it's a little bit more appeasing to the eye, but we can do it either way. Tilings that are periodic have patterns that are repeated throughout the tiling, and tilings that are aperiodic do not have a pattern that is repeated throughout the entire tiling. So last thing we want to do here is create a tiling by translating the quadrilateral shown, the one right there in the upper right hand corner. As you translate the quadrilateral, make sure the gaps left behind have the same quadrilateral shape. So I've taken this purple tiling here and it's kind of been rotated. And there are a lot of right ways you could go about this. And what I've done here is I've repeated it to the bottom and I've repeated it to the right. And notice it kind of has a little bit of a tilt to it. That's just so that the shape that's being repeated, the gap, the in-between white portion, is the same in all of them. So in this case, we have 2 different shapes that are being repeated here, the purple and the white. But to make it a tiling, it can't have any gap, it can't have any overlapping, and those need to be the same shapes. So you can go ahead and sketch that on your own notes. If you have any questions about perspective, symmetry, and proportion, let me know, and I'd be happy to go over them with you.